Hi, Nick McQuaid here, welcoming you to day 9, the beginning of week 3 of iste780, Data-Driven Knowledge Discovery. And today I'd like to talk about a couple of techniques, cross-validation and the bootstrap. And the idea of these techniques is that we have, if you recall, in fact, here, let me go back to chapter 2 here. Here's a picture from chapter 2 that gets referenced in today's chapter. And if you recall, we have this problem, the bias-variance tradeoff, such that if we use the training set, here's the training data, this is the test data, this is the mean squared error. What we want to do is minimize the mean squared error. And what we really want to do is minimize the mean squared error on the test data set. But the problem is that we just have the training data set. And if we if we make the training data set more and more flexible, we can keep reducing the error on it. But typically we'll find that that leads to an increase in the error on the test data set, which we don't have available ordinarily. So this is a big problem, and the techniques that we're going to talk about today help us to alleviate that problem. So the problem is we only have the training data, and what we would like to do is estimate the error on the test data. So the techniques for today basically use the training data as if it were the test data, and there are a couple of different ways of doing that. So let's look at those. The first way that's talked about here is really too simplistic, the validation set approach. So that approach, which is shown in this picture here, is that we take a portion of the training data, and we call that the training data, but then we take a portion of the training data, and we call that the test data. Or actually we call it the validation data, but it's essentially playing the role of the test data. So we build our model on the training data, and then we test it on the validation set, and we obtain a test error rate. We obtain the test MSE from here, and that's, it's got some advantages, in some ways appealing, but it's got a couple of problems, and the problems are described here somewhere. Here we go. The validation estimate of the test error rate can be highly variable depending on which observations we included in the training set and which observations are included in the validation set. So the test error rate is not necessarily a very good estimate. Also, it's likely to be an overestimate because what we've done is used a subset of the observations that we have. So we can expect that our method, that any methods that we use will perform worse in general the fewer observations they're trained on. So the fewer observations we train on, the more the higher the error rate. And so if we leave out a bunch of, we leave out some amount, say half here, I don't know if that's what's implied here, or maybe 1/4 or something like that, leaving all that stuff out and only using this is problematic. We would like to somehow be able to use the entire training set. That's the best set of data that we have available to build a model on. So can we somehow use the training data to build the model and also use the training data to test the model without running into the training data problems that I mentioned when we looked at this picture here? Is there something that we can do that may ameliorate this? And there are two main things that we can do. And the first one is depicted here. This is a special case of the first one, but I think it makes it for a good explanation to talk about it first. So in this one, this is called leave one out cross-validation. This is an abbreviation for leave one out cross-validation. So what happens here is, for the training data, we're going to use all but one observation to be the training data. And that one observation is going to be the test data. And then we do that over and over again n times. We have n observations. So each time we've left one out, so we have n attempts here. And then we take the average of the mean squared errors that result from this n procedures. And this works out pretty well. In fact, here's a picture of it in estimating the mean squared error for something with the auto data set that we used previously. We predicted miles per gallon as a function of horsepower and horsepower squared and horsepower to the third and horsepower to the fourth and so on. And so we get a fairly stable estimate of mean squared error here. So this is a pretty neat approach, cross-validating by leaving out just one item at a time. But it's a special case of another idea, which is to leave out k at a time. Oh, before we leave k at a time, let's take a look at this. So this is our estimate of mean squared error. It's the average mean squared error, n of n. So we take the sum of the mean squared error and divide it by n, basically, and that gives us our cross-validation estimate. And it turns out that in the case, just in the special case of linear regression, and I guess polynomial regression also, yeah, linear or polynomial regression, this formula holds. And so what you can do, where in this case, y hat sub I is the ith fitted value from the original least squares fit. So you basically only have to do one least squares fit, and then you just take all the leverages. You can calculate the leverage for each observation and use that in this formula, and you get the same result as the estimated mean squared error. Now, that's not such a big deal because in linear regression, it's pretty easy to get the mean squared error. So, but this can potentially be a potentially better estimate because it takes into account the extent to which an observation influences its own fit. Okay, so this indicates something better about cross-validation even for linear regression, but the power of it is certainly that it can be used in all kinds of techniques. See, it can be used with any kind of predictive modeling. And in those methods, it could be more problematic. Okay, but it's a special case of this. So here is k-fold cross-validation, where k is some number. In the case of leave one out, k is n. So here is five-fold. We're leaving out 5 observations, and so we run this 5 times. We have 5 training sets and 5 validation sets that act as if they're test data sets. And there's been a lot of empirical study of doing this that has found that 5 to 10, leaving 5 to 10 out, somewhere in that range, performs as well as leave one out. I think this is the average from using, let's see, this is 10-fold run 9 times. And you can see that it varies slightly, but it's remarkably similar to leave one out. The advantage that it has over leave one out is that you only have to run it 5 to 10 times rather than n times. And there are some predictive models, we haven't run into them yet. Linear regression can be run like that. But there are models, and in fact, there are regression models, depends on P, of course, and the type of regression, but there are just models that take a long time to run, and so it might be more economical of time and processor resources to do tenfold, fivefold to tenfold cross-validation. There's another advantage of there's another advantage. Oh yeah, here's some interesting stuff that should give an idea. So here we see the true MSE shown in blue. So this is simulated data. The leave one out as a black dashed line and the tenfold in orange. And what's important here, for the most part, sometimes approximating this is an important thing. But what's typically important is the choice. We want to be able to choose the amount of flexibility. This is this picture that I just showed you, by the way. This is for this data from Chapter 2, which we mentioned in Chapter 2 we would revisit later. And now we're revisiting it. And that was a smooth spline model. And we wanted to know how flexible we should make it, because we knew that we were going to have this kind of potential situation. And so the horizontal distance between these two x's is really what's important. Did we get very close to the actual minimum? Here, the fact that we've underestimated the MSE is not really a big problem, because the estimate that we've made is actually close to the minimum here. It's not. It's slightly higher than this. Here they're almost exactly even. Here they're almost identical. So this is a really good. These are worthwhile approaches. No, okay, so now in addition to the computational advantage, there is a bias-variance trade-off advantage to using 5 to 10-fold over leave one out. And it's described here that using k equals 5 or k equals 10 will lead to an intermediate level of bias. So this is a better situation in trade-off. So leave one out is better in just if we considered bias alone, but if we consider bias and variance, we will find that leave one out has higher variance than does k-fold, as long as k is less than n. So keep in mind that when if we're averaging n fitted models versus k fitted models, these models are necessarily less correlated with each other. The n models have to be highly correlated with each other. So the variance has to be lower for k-fold with k less than n. And in particular, there's empirical research on this kind of cross-validation that shows that 5 or 10 are good numbers to use. Okay, and then, there's a short section here on classification problems. So notice that we can do the exact same thing, except instead of MSE, what we're doing is taking the average number of errors. So this is the sum of the errors divided by the number of errors. And this is the extent to which we've placed our observation in the wrong category. So yi is not in the same category as y hat I. And we do the exact same thing. We can use logistic regression and apply cross-validation to that in essentially the same way. Now, here's this logistic. Okay, let me shrink this a tiny bit so you can see it. So this is also data from Chapter 2, I think, isn't it? Yeah, Figure 2.13 with the Bayes decision boundary. So this is using logistic regression to try to simulate this decision boundary here. And obviously, with a degree 1 polynomial, the linear case is not very good. Degree 2, still not very good. degree 3 and degree 4 are competitive with each other, and they're both pretty good. They both result in pretty low error estimates. So you can see the Bayes error rate is 0.133, and for these two, which is counterintuitive to me, this is the lowest, and this at 0.160 and 0.162. If you look closely at the observations on the boundary here, this looks better. This definitely looks better just on inspection of this sample, but the reality is that this is better. And here is a picture of what we just saw in terms of the order of polynomials used. So we find that the tenfold cross-validation error model finds the fourth degree polynomial is the best. The test error, so this is another cooked data set. The actual test error rate finds that the third degree polynomial is best, but they're not too dissimilar from each other. And if we look at the k nearest neighbor case with different values of k, so this is the different values of the number 1 over k, the ratio based on the number of neighbors used in the classifier. The tenfold cross-validation is not much different from the actual error rate, whereas k nearest neighbor, because it's so flexible, this just the training error rate just plummets. Okay, so I think that's about all about that. Now, an interesting fact is that the two of the co-authors of this textbook are the inventors of this other technique, the bootstrap. And so you would expect that they would come up with a really good explanation of the bootstrap. It is a little funny the way that they explain it. They use bits and pieces of several different examples here. So I think that's kind of hard to understand. So here's the example. We want to invest in two different financial instruments, instrument X and instrument Y. These could be two different stocks, for example, or two different portfolios or something. And we're going to invest a fraction of our money called alpha in one of them, and then the fraction of our money, 1 minus alpha, in other words, the rest of our money, in the other one. And this is a cooked data set, and somewhere here they give the actual variances that they used. The variances that they've used make it more attractive to hold a mix with slightly more X in it than Y. But anyway, this is unknown. So what we're going to do is to figure out how good our estimate of the best alpha. See that we get these ranges of alpha in here. So this would suggest that 53% is invested in X, and this would suggest that 65 or 66% is invested in X from simulated data. And it's hard to tell here in the simulated data. I think it's this one is pretty intuitive. You can see that there are no low X's in this one. But the other ones, you really can't eyeball them. You really have to do the calculations to get these numbers. I would not have guessed that this would be the other high one, for example, or that these two would necessarily be the low ones. Okay, so what we're going to do is use the bootstrap technique to, where am I here? So what we want to do is simulate paired observations, estimating alpha and doing it 1,000 times. So we get 1,000 estimates for alpha, and here's a histogram of those estimates for alpha. And I think the vertical line is the ideal line. And over here we see the bootstrap estimate. So if we so here they actually, because it was a cooked data set, they could take 1,000 data sets, from 1,000 simulated data sets from the same population. Taking 1,000 so the bootstrap ones are all coming from the same data set. And the histogram is remarkably similar, and the choice of the best alpha, which I think is it looks like it's 0.6 exactly here. The choice of the true best alpha is, in roughly the same place in both of these cases. And the box plots of the true and the bootstrap are almost indistinguishable. So the true obviously has the correct median. The bootstrap median is very close. So another piece of an example. So that's part of an example. The other part of an example here shows what's actually going on in the bootstrap. That example doesn't show technically what's happening. So we can take a look in here and see exactly what's happening. So here we have a real data set. This real data set only has 3 observations in it, and each observation has an X and a Y. And to bootstrap from this data set means to take a fake data set from which we randomly draw examples of these with replacement. And anytime that we draw an X, we also draw its matching Y, because otherwise we would get total nonsense. If we paired this X with this Y, the data set wouldn't in any way resemble the original data set. But we can take these, and so here we've taken this one twice, and we've taken observation number 1 once, and we formed a new bootstrap, what is called a bootstrapped data set, pulling this data set up by its own bootstraps, in a sense, is where the intuition of the name comes from. And so they do this for some large number. Here we have number 2, number 3, and number 1. Here are 2 copies of number 2 and 1 copy of number 1. So this is sampling with replacement. So when we sample irrespective of whether we've already sampled one of these. So we get all these bootstrapped estimates, and we find when we do that we wind up with parameter estimates that are really close to the real ones, potentially. So this is a huge big deal, and it's particularly big because we can use it on anything. So at any place where you have data and you want to estimate some parameter of that data set, these are optimal combinations. So these are predicted optimal combinations. So this is not quite the same thing as this example, but but I think it helps to explain it. So that's pretty much it. So now what we're going to do tomorrow is a lab on cross-validation and the bootstrap. We can actually use these. And these are techniques that are contemporary techniques. These are techniques that were not possible before we had relatively fast computers. So this is kind of the newest ideas that we've explored so far. Thanks for your attention, and we'll see you tomorrow.